This is part 2 of Unit 6, Lesson 2, Riemann sums, summation notation. In this part of the lesson, we are just going to go through some examples to go back and forth between writing a definite integral in terms of a Riemann sum or a Riemann sum in terms of a definite integral, and then evaluate them. I'm not going to do the evaluation step. I will put the answer there, but you can evaluate either the definite integral or the Riemann sum, but you really should do both forms to make sure that you know how to do both types in your calculator, and you can check it against the value that I have here so you know which one is the correct one if you do get two different values. Okay, so the first example 6 is we're going to go from definite integral form into a Riemann sum. So we are looking at the integral from 2 to 4 of 3x squared minus 1 dx. So a couple things we have to put together is our delta x and our x sub k. So from the definite integral, we can see that a is 2 and b is 4. So that means I can find my delta x, which is b minus a over n. So I'm going to have 4 minus 2 over n. So my delta x is going to be 2 over n. So that's the first thing. Next thing is I want to find my x sub k. And x sub k comes from a plus delta x k. So in our case, this is going to be 2 for a plus 2k over n for delta xk. So now I can write my Riemann sum. So my Riemann sum is going to be the limit as n approaches infinity of my summation of k equals 1 to n of, now substituting it in the function, we have, let me put a box here, 3 times, and that's going to be my x sub k, and in this case I'm going to write 2 plus 2k over n squared minus 1, and then that has to be multiplied times the height of each rectangle, which is 2 over n. Okay, now I can't really substitute that any unless I want to multiply out that quadratic, and I don't really feel like doing that. It's not really necessary, so I'll leave it like this. And to check it in your calculator, the value you should get is 54, both for the integral and also for the Riemann sum. So make sure you can do both of those. Okay, next we're going from negative 2 to 0, the integration of x plus 3 squared dx. So in this case, a is negative 2, b is 0, so delta x is b minus a over n. So that is just going to be positive 2 over n, because we're going to have minus a negative. And then so we have our delta x here. And then our x sub k is a plus delta xk. So our a is negative 2 plus 2k over n. All right, so now writing our Riemann sum, I'm going to use a different color just to differentiate it here a little bit. So n is headed to infinity of the summation k equals 1 to n. And now we're going to fill in our function. So our x plus 3 is now going to be x sub k plus 3. So we're going to have negative 2 plus 2k over n plus 3. Now here I can do a little simplifying, squared times 2 over n. And in simplifying this, I'm going to get, I wrote kind of big, so I'm going to write over here, the limit as n approaches infinity of the summation of k equals 1 to n. And inside, we're just going to have 2k over n plus 1 squared times 2 over n. And the answer to that, if you do this summation or you do the definite integral, you should get 26 over 3. Or you can make the decimal equivalent. Okay, next one. is now a trig function, but the procedure is not any different. So in this case, a is 0, b is pi. So delta x is b minus a over n. So we're going to get pi over n. So that's our delta x. Now our x sub k is a plus delta xk. So in this case, a is 0, so we just have delta xk. So we're going to have pi k, that's a pi symbol. It's supposed to be a pi symbol. Pi k over n. All right, so now we can write our Riemann sum. So we're going to have the limit as n approaches infinity of k equals 1 to n. And now, I don't really need the parentheses there. We're going to have sine x. And instead of x, we have x sub k, which is just pi k over n. And then this is multiplied times pi over n. And if you figure this out for an answer, you're going to get 2. Okay, now we're going to go the other way in the next example. This time we're given the Riemann sum, and we're supposed to write the definite integral and then check the answers. So you want to identify certain things here. So in the first one, what you want to recognize is that this is our ax. I'm sorry, our x sub k. Okay, so there is our a, and that is going to be our delta x times k. Okay, so that's what you want to recognize there. So we can see that a is equal to -2, and our delta xk is going to equal 5k over n. So we can see that our delta x is 5 over n. Now what do we need to know that for? Because we want to work backwards to get b. So we know delta x is b minus a over n. So our b minus a has to equal 5. So we have b plus 2 has to equal 5 because we had minus a -2. So b is going to equal 3. So now we're able to write our Riemann sum, because right here then that is also our delta x. Not a Riemann sum, our definite integral. So our limits are going to be from -2 to 3, and our function is 5. And now instead of writing that expression for x sub k, we're just going to write x, and then we have the -1, and that's going to be dx. And again, you should evaluate both forms to see what you get, and you should get 15 over 2 or 7.5. Okay, going through the next one, same thing. Here is our x sub k, and here is our delta x. So here's our x sub k, and here's our delta x. Okay, so the last thing there has to be, that's your a there. Okay? Whoops, I've circled the wrong thing. That is not your a. A has to be part of x sub k. This is your a. Okay. So now we have that a is -2. Delta x is 2 over n, so we can use that to find our b. And we know our x sub k is 2k over n minus 2. So you can see your 2 over n in that as well. All right, so we know that b minus a has to equal 2. So b plus 2 equals 2. So b is 0. So now we can write our definite integral. So our lower limit is -2, our upper limit is 0. Then we have that 3 times our x sub k, so that just becomes x plus 4, and that's dx. And when you evaluate this, you get 2. Okay, on the next page, there's one more of these. And again, same thing. You can see right away looking at these. This is your delta x, and this is your x sub k. And if you notice, there's no addition or subtraction there. So that tells us right away that a is equal to 0. So then delta x being pi over 6n tells us that our delta x, remember, is b minus a over n is going to be, so that means that b has to equal, if I factor out b is going to have to be pi over 6 to get the pi over 6n. Okay, so writing our definite integral notation, our lower bound is 0, our upper bound is pi over 6. So we just have cosine of x sub k in our Riemann sum, so that's just going to be cosine x dx. And if you evaluate that, you get 1/2. Okay, last example. So in this example, a Riemann sum in simplified form needs to be unsimplified before translating it into a definite integral. So if you look at the one that's given there, we have the limit as n approaches infinity of the sum of k goes from 1 to n of k to the third over n to the fourth. So we have to peel out of there the delta x and our x sub k separately so that we can break that apart to get our limits of integration. So looking at letter A at the bottom, what I can do first is I can rewrite this summation notation in a different form, so maybe it's a little easier to see. Like I can write this as 1 square root, so I have k over n squared. Okay, now what, I'm sorry, n to the third. Getting ahead of my brain. It's getting ahead of me. So I can really think of that part as the square root of k over n times 1 over n without the square root. Because if I were to put this 1 over n into the square root, I would have to square it. So now I can see that my delta x is 1 over n, and my x sub k is going to be k over n. So now I can write my integral, because now I can find my upper and lower limits, because a then is going to be 0 and b is going to be 1, so I get that 1 on top. So I'm going to have the, it's going to integrate from 0 to 1 of the square root of x dx. And that is going to be 2/3 when you do that. Okay, next one. Now this one's a little more tricky because the summation notation isn't written here, so I want to like unwrite it. I want to put it back in its summation notation so I can identify my delta x and my x sub k. Okay, so what I see here is that I always have an x cubed on the bottom, but the top is this perfect square, and then I can see it here that I have a perfect square over n cubed. So I could factor out a 1 over n, and then I'm left with some k, because remember your index goes from 1 to, this would be 2 squared, 3 squared. So that's your k over n squared. So now that I can see that, I can see then that my delta x is 1 over n, and I don't have any other terms added or subtracted, so I started at 0, so that means b has to be 1, and then my x sub k is k over n. So now I can write my integration. So my integration is going to be from 0 to 1, and my function is going to be, I'm squaring, so it's going to be my x sub k squared dx. And when I do this, I get 1/3 as a value. And then finally the last one This one's a little tricky. We want to rewrite this. If you see that this term here has a common factor of 8 minus n that you can factor out, so you get 1 plus 64k over n. So what we've done is we found our delta x. That's our delta x, and this is our x sub k. So here we can see that we have an a of 1. A is going to be 1, so delta x being 8 over n. That means that b minus a over n is going to be, so our b minus a has to be 8. So we have b minus 1 equals 8. So b is 9. So we have that. And then, oh, I wrote that wrong. I'm sorry. This should be 8k. Because I have to get a 64 when I substitute that in there. Writing my definite integral, so I'm going to go from 1 to 9. So now that's my x sub k, so that's going to be ln of x dx. And when I do that, I get a value of 11.775. Okay, so that's the end of lesson 2. We're going to talk about this in class as always, and I'll answer any questions then.